Hi everyone. So today is the April 13th lecture. So we're going to talk about a new things. It's called a solid space. Okay. So this is a solid space. It's basically the solid space is extension of the LP space. Okay. And also why we study solid space, because this is a very important tool for the analysis and also for the PDE. So this is many applications to PDE. So when you are going to take a PDE class later, you will see that this is a solid space. It's very useful tools. Okay. So today, what we're going to begin to introduce the solid space. So we'll begin to consider a very simple case first. So we're going to consider the solid space over a very simple domain, over interval AB. Okay, and interval AB is in R1. So look at this simple case first. Then we make extension to the multidimensional case and extend to the general domain. Okay. Now, in order to look at the solid space, we need to define what we call the weak derivatives. Okay. So let's first review what we call the strong derivative. Now, suppose you think about a function fx. And the fx is in C1ab. Now, what I mean by a function C1ab? So this means this function is differentiable at every point of the interval AB, and also the derivative is continuous. So this is basically a collection of all the continuously differentiable function over the interval AB. All right. Okay. So how do we define such a function in C1? So there's a traditional method, which is actually the pointwise definition. So let's say that you can think about it this way. So the fx, the derivative. Okay, so using traditional definition, so this is the limit, delta goes to 0, then f x plus c, the delta, minus fx and delta. So you look at the difference quotient. So this one exists. This one exists for all x in AB. Okay. And also, another condition is that the derivative it's not just exist, but also continuous. It's also continuous. So that's the traditional way to describe a function fx in C1 function. Okay. But however, this definition is pointwise definition. So what we want to talk about is we're trying to find out another definition for the f, how to characterize function in C1 using the global definition. So we're trying to think about how do you come up with such thing, global definition. Okay, so that's the first step, and we have to follow in order to define the weak derivative. Okay, so let's make some observation. Okay, so let's pick a function. Let's now define function phi x. Now phi x is considered a testing function. So this phi x is always considered to be a C0 infinite AB. So it's infinitely differentiable and also support. So the support of phi, okay, is actually inside the AB. Actually, the closure of the support of phi is in AB. So this means this is what we mean by C little zero here. The little zero here basically means the support. This fact support is inside. So in particularly, so this phi function actually is going to be vanished at the point A and B. So this function is going to be considered as a testing function. Test function. So this is our tool, okay, to define the derivative globally. Okay. Now let's make some observation. Okay. Now suppose I take fx and multiply the phi x together. And now you can see that this product is a product of two differentiable functions, right? So therefore, I can take the derivative to the product, and it follows from the product rule. It's just equal to f prime x times phi x, and plus the fx times the phi prime x. So this is something I know. We know follows from the calculus. Okay. Now what we're going to do here is that now the next I'm going to perform the integration AB on both sides. Okay, and then you look at the integration on the left side. You can see there's a complete differentiation inside the integration. So therefore, you remember something called the fundamental theorem, right? Fundamental theorem of calculus. Using fundamental theorem of calculus, you can see that the left side, if you do the integration, okay, the left side equals to what? Equals to using fundamental theory, so this is just the FB and phi B, then minus FA and phi A. Okay? And this is the left side. Now this left side must equal 0 because you can see that, I don't know what the value of FB and FA is, but I know that I do know that phi is complex supported. So this function is vanished at the endpoint. So this means the phi B equals 0 and phi A equals 0. So therefore, the right side must equal 0, no matter what the value of f will be and A and B, right? So this integration on the left side equals 0. So this means integration on the right side is also equal 0. And I can write the right side in a different way. So this implies that now I'm getting a very important formula. So f integration from A to B. And so I put this term first, okay? And moving this term, the first term to the left side. So this term still on the here. So I put one side, so this means that, oh, this term on the left side. So this is fx times the phi prime x. Okay? So now this equals to the other term, right? The other term will to the other side will carries the negative sign. Let's become this, AB. And f prime x and the phi x. Okay, so I have this. Now this thing is important. Okay, this is our observation. Now this can be considered identity because this is true for every such phi. For every testing function set by this condition, this is true. So from here you can see that I can actually give a global definition of the derivative. Okay? Now how do you define this globally? You can see that for every f, so suppose you have an f here sitting here. Now suppose you can see that there is another function here in place of another function, maybe I call g, okay, in place of this guy. Okay, suppose I have another function g which is continuous, and to make these things hold for every phi. And then you can see that this g can be considered as the global derivative of the f prime. However, here we have justified it. So therefore, I'm going to write the global definition of the derivative first, and then I'm going to justify it, okay, using here. So let's remove this. Okay, all right. So let's put a new definition here. Okay. Definition here. Now, what we say is that for f is in the C1 AB. Okay. Okay. So if there exists a g is in now g is supposed to be in place of f prime. Okay. It's a continuous function. Okay. C0 AB, and such that this integration holds, and integration A to B, and f x and the phi prime x is equals to the integration AB equal to minus, okay, there's a minus sign here, it's important, to the gx times vx, okay, for every such a phi. Now, if such a g exists, and then this g is considered to be the derivative. So then we're going to g is f prime x, okay, in the global sense. Okay, so this is considered as a new definition for the derivative. But however, we need to justify it. The justification, from the justification, we're going to see that if this g, if g satisfies this condition, such a g exists, then this g is not going to equal to something else. It's always equals to the derivative, the original derivative at prime. So what we're going to see is that there's a theorem here, a new theorem here. The theorem we're going to show that basically says, I'm not going to describe the theorem in detail. I'm going to prove it, but I'm not going to put a detailed statement. What we're trying to use this notation, which is already there, we're going to show that this gx, okay, if it exists, is always equals to f prime x. So this is a fact. Now, because of this fact, you can see that I can use this as the new definition of the derivative, right? Otherwise, you can see maybe exists such a g satisfied this, however, this g may not be equal to f prime. Then the definition is not going to make sense. So what we're going to see is this is always true. This is always true. Okay. So I know that suppose f is in C1, okay, then I know that if I put here is f prime x, okay, then this is always true for every p, right? Now here we have another g here. Also make this happen for every p. So therefore, these two integration on the right side were equal to each other. So this conditions will imply that the integration AB, okay, the gx, okay, minus f prime x, okay, times the phi x is equal to 0 for all phi x. I will have that, right? Suppose I have a g satisfied like this, then you can see that the f prime is already satisfied. So therefore, this difference should equal 0. Then from here, we're going to show that, and gx must identically equal to fx. So then you can see that g is considered as the global definition here. Now the proof is very simple here. Now let's say that suppose I'll just consider, okay, now use a different color, so I'll just consider this function, this different function, to be Lx. Lx. Now Lx is what? It's a continuous function, right? Because g is assumed to be continuous, and prime is continuous. It's a continuous function. So this continuous function, when multiplied to any test function, it's always equal 0. And this will imply that we're going to show that this continuous function is identical equal 0. Now, if I can prove this, so far it's questionable, right? Suppose I can prove this will imply this. Okay, no problem. The proof of this can be done in a very simple demonstration. So I'm going to draw a picture here. So suppose you have this coordinates here. So this is from A to B, okay? And here you have an L function, it's continuous. And multiplied to any phi is equal to 0. Okay, so let's say that I'll pick a C. So C belongs to AB. I just pick an arbitrary point C, okay? And you look at LC. So LC, if LC equals 0, that's fine. Now suppose LC is not equal 0, okay? We may assume that this LC is greater than 0. Because in the other case, where you see negative, the proof follows the same line, okay? Now, here we're going to see that you are going to get a contradiction, okay? Why? Okay, let's say C is here, okay? C is here. And then suppose, so LC is greater than 0, so the value is here. So L function is like this, right? So now since L is a continuous function, so therefore it's going to be strictly positive. It's going to be strictly positive in a neighborhood of C. Okay, so this neighborhood I can define like this. It's from here to here. So this is C minus delta, and this point is C plus delta. It's going to be something like this. Now I'm going to choose a phi, okay, properly to reach that contradiction. So how do I select the phi? So I'm going to select phi like this. I want the phi to be actually always equal 0 outside. Okay, phi equals 0, and then continuously out equal 0 goes inside a little bit, and then the phi will stay as positive like this for the phi. And so at the C value, so when you reach to the C and this phi function, the phi 1, phi C is exactly equal to 1. I can create such a single function in a very simple way, okay, set by this condition. Now once I have this phi, so I know that the integration from AB and the Lx times the phi x, okay, I know it's equal 0, right? Now because this function, this phi will be equal 0 outside of this small interval. So this integration reduced to C minus delta, C plus delta, the Lx and the phi x. Then if you look at this integration again, you can see that this function inside this integration, the integrand, is now negative. It's actually greater than or equal to 0. Okay, but the integration equals 0. So this means that this function has to be identical equal to 0. So therefore, the Lx times phi x has to be identical equal to 0. Okay, so suppose you plug in the value x by c, so you have Lc times the phi c is equal to 0. So this is a contradiction because the Lc at the very beginning we can see Lc is assumed to be 1. Lc is greater than 0, right? And the phi is chosen to be 1, at c. So therefore this thing is not going to be equal to 0. So this is a contradiction. So this contradiction shows that the L function has to be identically equal to 0. So this shows that the G function is not another function, it's just the price. So this justifies that I can use this to redefine the derivative in this way. Okay, so that's the starting point of define the weak derivative. Okay. And now, if you look at here, so when we give this global definition, I give a global definition of this the C1 function. There's two conditions involved here. Two conditions. So here is called for every p. Okay. There's two conditions. Okay. The first condition is that I know that when we define this global derivative, so this guy f in C1. That's the first condition. Okay. Another thing is we're assuming the G function here. G function here is C0, is a continuous function, okay? Now, suppose I remove both conditions here. And then maybe this identity still holds for some other function, right? If that happens, then this function is not going to be the strong derivative in the traditional sense, but we can consider this kind of weak derivative thing. So therefore, I can define it this way. So there's another definition here. So this definition is about the global definition of the C1 function. Here is a definition for the weak derivative, okay? And now let's just think about a very weak function like f is only in L1, AB. Okay? So if, okay, they exist. So L1 function, the function is just integral function, and the function may not carry any derivative. Okay? So suppose there exists G is also in L1. Okay? And such that. So I call this a star. The star hold for F and G. And then if this happens, so in this weak defense, So f is just L1, the g is also L1. Then we call that the g is the weak derivative of f over the interval AB. So that's the definition of the weak derivative, the weak sense. Because in this case, well, we get existence of g, it looks like derivative, but really the f itself may not carry any derivative in the traditional sense. Okay, so this the first step where we define the solid state, and we need to understand what is meant by the weak derivative. Okay. Now here we are going to see example first before we move on. The example shows that such things does exist. So this means that you can always find function which is not in C1, but however, the derivative exists in this sense. So that derivative is the weak derivative. So we're going to see example, okay? See example. So I'm going to leave this here, okay? I'll still leave this formula here. And we're going to see this example. The example is that you have a function fx, okay? Fx is not in C1, okay, but it's only on C0. It's just a continuous function. It's just a continuous function, okay? But however, it is piecewisely C1. Okay, so here's the situation. Okay, like A to B, and there's a point C here. So the function is going to C1 here. But suddenly, the function is also going to be in the second interval, it's also C1. But however, when you connect these two pieces of function together, you can see there is a corner. It's a corner. So this means that the function is a continuous function. However, it is not going to be differentiable at every point of inside AB because the function is not differentiable here. It's not differentiable here. Okay. So we're going to see that for such a function which is not in C1, the weak derivative exists. Okay, so I can define this function like this: f x in C1 and A to C, and also in C1, C to B. Okay, like this. Okay. Okay. Now, actually, I can construct the weak derivative in this sense because I can see that the derivative exists on AC and that the derivative also exists from C to B. So I put these two derivatives together to make the weak derivative. Okay, so I just take the gx, okay, and to be the f prime x, x belongs to AC, and also equal to fx because these two, the derivative of fx is not continuous at C. Okay, so I have to define this pointwise. So this is equal to x belongs to C and B. So this is a discontinuous function because of the corner here. Okay. Now we're going to see that this, even though this is discontinuous, then this guy still be the weak derivative of this f in this definition. Okay. So what does it mean? So what we need to verify? We need to verify that this identity holds for every phi, right? Okay, so this is what we're trying to do. Okay, so we're going to look at the left side first. So left side is integration AB. Okay, AB, then this the f and the b prime dx, right? And we're going to show that this equals to the other side with the minus sign. Okay, so let's work on the left side. So I'm going to break this integration into two pieces. So A to C, f b prime, then plus integration C to B, f b prime, okay? So naturally you can do this. And then I can rewrite this. I'm going to work on the inside. So here, I still A to C, but now I'm going to represent this by F times phi, the derivative minus, here I'm using the product rule, okay, the F prime. And the phi. Now, here I can use the F prime because I'm not working on the entire interval A to B. I'm only working on interval from A to C. So therefore, in this smaller interval, the function is C1. So the F prime exists, right? I'll do the same thing on the second one. The second one is equals to and C to B. Then you can also write this way, F the minus F prime B. Okay, I'll write these both ways. And now I'm going to work on these two parts first. I know that they are the complete differentiation, so I can use the fundamental theorem of calculus. Okay, so therefore this is going to be equals to, so the first one, using fundamental theorem, is equal to F C phi C, okay, minus F A phi A. Right? And I also, so I'm going to put these two terms together. So the next thing I'm going to work on is this one, okay, using the fundamental theorem. So this is equal to FB, phi B, then minus FC, and the phi C. Okay. Then I put these two integrations together. So then I plus, then minus, okay, there's a minus sign here. So minus AC F prime B minus C to the B F prime C. Okay, so this is what we got. Okay. Now, here, I'm going to look at these four terms. And we're going to show that these four terms all equal to 0, all cancelled. Why? Because you remember here, for the F function here is piecewise, F is piecewise defined. So when we evaluate this guy at C point, so basically we evaluate this from the right side. And here, when we evaluate this one, we evaluate it from the left side, okay? And actually, this one we evaluate from the left side. This is on the right side, okay? Now phi is a continuous function, so phi C equals phi C. But F function is continuous, so no matter how you evaluate from both sides, they're still equal. So these two terms cancel. And also on these two terms, I know that phi A equals 0 and phi B equals 0, right? So this also equals 0. They're all canceled. So therefore, there's only left to the other two terms here. But then I can combine this one. I can combine this one to be the minus integration AB. Now, when you combine this, you cannot combine F prime together unless you use another notation, because F prime is not continuous function. It's not defined as C, right? So therefore, but however, you can see that G is defined here. G is defined piecewise by the F prime, right? So therefore, if you combine these two integrations, you can write this to be just the GX times. It's just equal to G times C, nothing else. It's G times C. So now you can see if you from the very beginning, so we begin from here, and now it's all the way equal to here. They're all equal. So this just showing that G is the weak derivative of F. And in this example, you can see that even though F prime does not carry the global C1 derivative, the derivative in the traditional sense, but the weak derivative still exists. Okay, so that's why introduce in weak derivative makes sense. All right, so this is this example. And now next thing we will now is going to define the Sobolev space over this interval, okay? So what we're going to define is a new space here. The new space is called, so I'm also going to remove here. So the new space is going to call it W, called W1P on interval AB. Okay, so what is this space? This space is equal to all the functions in LP AB, such that, so here, one thing you need to remember that if you here P is greater than equal than 0, okay? P is greater than equal to 0. L is greater than equal than 1. Now if you have a function in LP, since our domain is finite, so it's easy to show that this F is in L1. Actually, the function is also in L1. Okay. Now if you have a function L1, so you can introduce a weak derivative, right? But in this case, we want to show that we want to consider all such functions that they exist the weak derivative, but I use the F prime to indicate that's the weak derivative, okay? And we want this weak derivative not only exist, but also, so there's strong condition, they're also in the LP. So when we say the weak derivative exists, so this weak derivative is basically maybe just L1 function, right? But here we want this to be the LP function, okay? So I'm going to consider this space. This space is just called sorvative space. Well, this is one of the sorvative space. Okay, there are many sorvative space, and over the interval AB. And one thing you can see that this sorvative space actually depends on P, right? It depends on P. So if you change the P's value, the value of P, of course you're changing the space. Okay, here we just assume that we are fixing one P, and we define the space. So this space is well defined. It's well defined space. Okay. Now, so this is just a space, okay? Now we're going to introduce the norm of the function in this space. So the norm is denoted by 1P. So the norm is not going to be LP norm. It's going to be equals to the LP norm of F and plus the LP norm of F prime. Because both are in LP, so therefore I can just add this two norms together, okay, to define the LP norm of this function in this space, in this new space. And we're going to see that this norm is really a norm, so this space will become a norm space. Why? Because in this case, we can actually prove the Minkowski inequality. 1P is less or equal than F 1P plus the G 1P, or you can call it triangle inequality. Okay, so it's very easy to prove this, because if you replace F by G and here, so you have F plus G here, F plus G here, right? F prime plus G prime here. For the LP function Minkowski inequality hold. So apply this inequality on both terms, so you have to get this. So this is very simple. Okay, so this shows that this space is a norm space. It's a norm space, okay? But we haven't shown this space is a Banach space yet, because we haven't shown the completeness of this space. Okay, in a moment we're going to show it's complete. Okay, now before I can move on to the completeness, so I'm going to have a remark. So in lots of textbook, they define the norm in a slightly different way. Okay, they define norm. So I'm going to just invent another notation, okay, like this, to be integrations AB Fp plus F prime P and the norm P. Now if you check the detail carefully, you can see this guy is not equal to that, because this guy, the LP, the 1 over P, the power is applied to individual term, not applied to the summations. Okay, so these two are different. In some sense, this guy, if you still, you can call this as a notation, okay, but really the space is not a normal space in this sense. Okay, but however, we can show the equivalence. the equivalence shows the following. It shows that if you look at this new norm, the norm with the quote, okay, so this is like 1p. It's controllable by a constant times the norm we defined in the first place on both directions. Okay, so we call this a C1, this is called. So this means that these two things are equivalent. Okay, now the equivalence of these things will introduce that, will tell us that actually, if you look at the distance introduce the new distance, I'm going to call this new distance, okay? And this new distance of F and G, for instance, is controllable by the distance introduced by this norm. So it's a distance of F and G. And so therefore this is also controllable from the other side. So C1 distance. So when we introduce a norm like this is not really a norm, but however, it's equivalent to this thing. So therefore, what we really have is the equivalence of the distance. So this means that the topology behind these things is the same. And that's the most important things in analysis. So that's why people don't care whether we can use this definition or the other definition. As long as they're equivalent, everything's fine. Okay, so that's one thing. And now we're going to see that now we're here, we always use this new definition, okay? So what we're going to see here is that under this norm, we're going to see that this space, the solid space, is really a Banach space. What does it mean by is that we're going to prove the completeness of this space, okay? Okay, now how do you prove the completeness? We're going to show that every Cauchy sequence in the space is a convergent sequence, right? So let's pick a Cauchy sequence, let's say. Like this. Cauchy sequence like Fk in the W1P. Okay. Now, when we have a Cauchy sequence here, so what does it mean it is Cauchy? It means that if you look at the distance, K minus FL and 1P, this goes to 0 when the K and L both goes to 0. Okay, now you can see that this norm, 1P, is sum of these two individual norms. So because of the relationship, so this goes to 0, then you can see if a individual norm still goes to 0, because it's less than that, right? So this will imply that this Fk, if we view this Fk in LP sequence, so is Cauchy in the LP sense. Okay, and also if you look at the derivative sequence is also the Cauchy in LP. Okay, so this is what we got. Now, if you have a sequence in LP is complete, it's a Cauchy, then our LP space is a Banach space, is complete. So therefore, there must be functions. So Fk should goes to a function in LP, right? And at the same time, the Fk prime, okay, is also going to converge into something else. So what we call G is also in LP. Okay. And now let's look at this identity here. So I know that Fk and Fk prime, they satisfy this identity through the testing function, right? So this means that if you look at integration AB, then Fk times the phi prime, so this equals to minus integration AB, the Fk prime times the phi. And this is true for every phi. Okay. And now you can see this integration, okay, so this is a very smooth function, it's a bounded function, the phi prime. So if we let the k goes to infinity on both sides, then you can see since the Fk goes to F in the LP naught, so using the holding quantity, it's very easy to show that if you let it K goes infinity, so the left side what goes to the AB and F to the V prime. Okay? And the right side, for the same reason, it also goes to, it's also with a minus AB, the F equal to G and the V, right? So therefore, because they are originally for each K, they are equal. So therefore, you can see when X goes, K goes infinity, then this is also equal. And also it's equal for every V. Okay? So this simply shows that this Cauchy sequence has a limit in the W1P space because of this. And this limit is F. And from here you can see the F carries the weak derivative G is also in LP. So this means that, so this shows that WP, so now you can conclude W1P is complete. Is complete. Okay. So this shows that this space actually is a Banach space. Is a Banach space. Okay. So this is the introduction in the one-dimensional case. Now next time we're going to continue. So before I move on to the multi-dimensional case, to the general case, I'm going to introduce what we call higher order Soviet space. You can see this Soviet space is actually a first order Soviet space because we only deal with the first order derivative, right? So what if you can think about second order derivative, the third order derivative? All these derivatives can be defined weakly, in the weak sense. So next time we're first going to make some more discussion about the higher order Soviet space over the AB. Then we're going to extend it to the general case. Okay, so this is today's lecture. See you next time.